I told you once about a disagreement between Einstein and me that lasted years, one that never resolved cleanly while either of us was alive to keep arguing about it. Einstein believed the universe couldn't be as strange as quantum mechanics suggested, that beneath the probabilities and uncertainties, some deeper hidden layer of reality must exist, one where particles have definite properties all along, waiting to be discovered rather than created by the act of measurement. I want to tell you what happened to that belief decades after both of us were gone, because the answer is more decisive and in some ways more strange than either of us ever got to see confirmed. The specific idea Einstein was defending has a name. Physicists still use today: local realism. I want to break that phrase apart because both halves of it matter enormously to what eventually got tested. Realism in this context means that physical properties exist independently of whether anyone measures them, that a particle has a definite spin, a definite position, whether or not an observer is looking. Locality means that no influence can travel between two separated objects faster than light allows, meaning whatever happens to one particle cannot instantaneously affect a distant particle without some signal traveling between them at or below light speed. Einstein, working with Boris Podolsky and Nathan Rosen in their famous 1935 paper, argued that quantum mechanics, as Bohr had formulated it, violated one or both of these principles, and that any theory violating them so directly must be incomplete, rather than a true, final description of nature. For decades after that paper, this remained, as I told you before, philosophical territory more than experimental territory. Both Einstein's hidden variables position and Bohr's view that reality genuinely doesn't have definite properties until measured made the same experimental predictions in every situation physicists could actually test, which meant the disagreement, however deep, couldn't be settled by any experiment then available. It sat as one of the most important unresolved questions in the foundations of physics, argued about at conferences, written about in papers, but never decided by direct measurement. That changed because of a physicist named John Stuart Bell working at CERN in 1964, nearly 3 decades after the EPR paper, and I never had the chance to fully absorb what Bell had done, because I died in 1967, only a few years after his work was published, before its full significance had really been recognized by the broader physics community, let alone tested experimentally. Bell did something genuinely remarkable, something neither Einstein nor Bohr nor anyone else arguing about this question in the 1930s had actually managed to do. He found a way to turn a purely philosophical disagreement into a testable numerical prediction, a mathematical inequality, now called Bell's inequality, that any theory satisfying local realism, any theory built on Einstein's hidden variables assumption, would have to obey. And crucially, Bell showed that standard quantum mechanics predicts situations where this inequality would actually be violated, where the measured correlations between entangled particles would be stronger than any local realistic theory could possibly produce, no matter what hidden variables you tried to introduce into the theory to explain them. I want to walk through the basic logic of what Bell showed, because I think the elegance of it deserves to be understood plainly rather than simply asserted. Imagine a pair of entangled particles created together and then sent flying apart in opposite directions. The same basic setup Einstein, Podolsky, and Rosen originally imagined in their 1935 paper. You measure some property of each particle, commonly a property called spin, or in later, more practical experimental versions, the polarization of entangled photons, using detectors that can each be set to measure along different chosen angles. If Einstein's hidden variables picture is correct, each particle carries a definite predetermined answer for every possible measurement angle, established at the moment the particles were created and separated, before either measurement actually happens. Bell worked out precisely how correlated the measurement results at different detector angles could possibly be under this assumption, and derived a strict mathematical limit, a specific numerical inequality that the correlations could never exceed, no matter what hidden variables or predetermined properties you assumed the particles carried. Quantum mechanics, however, predicts something different. For entangled particles measured at specific combinations of angles, standard quantum theory predicts correlations that exceed Bell's limit. Correlations stronger than any theory built on Einstein's assumptions of realism and locality could ever produce. This was the genuine breakthrough Bell provided. For the first time since 1935, there was an actual number you could measure in a laboratory that would tell you directly and unambiguously whether Einstein's picture of the universe or Bohr's picture of the universe more accurately described how nature actually behaves. The first serious experimental tests of Bell's inequality began in the early 1970s, shortly after my own death, conducted by physicists including John Clauser, working initially with Stuart Friedman at Berkeley, the same university where I'd spent so many years of my own career. These early experiments faced serious technical limitations. The detectors and photon sources available at the time weren't yet precise or efficient enough to close off every possible alternative explanation for the results, leaving what physicists call loopholes, technical gaps in the experimental design that a sufficiently determined defender of local realism could, in principle, exploit to argue the results didn't yet definitively rule out Einstein's position. The most historically significant of these early experiments came from a French physicist named Alain Aspect, working through the early 1980s at the University of Paris, whose experiments introduced a crucial refinement, rapidly switching the detector angle settings while the entangled photons were already in flight, specifically to close off what's called the locality loophole, the possibility that some hidden signal traveling at or below the speed of light could pass information between the two detectors in time to influence the measurement outcomes in a way that would fake the appearance of a genuine quantum violation. Aspect's results, published in 1982, showed a clear, statistically significant violation of Bell's inequality, matching quantum mechanics predictions and disagreeing with what any local, realistic hidden variables theory could produce. I want to be honest, in the spirit of careful physics, rather than premature celebration, about why this wasn't yet considered the final, absolutely conclusive word, and why the experimental program continued for decades afterward. Aspect's experiments, sophisticated as they were for their time, still left certain narrower technical loopholes theoretically open. Questions about detector efficiency, about whether the specific subset of photon pairs actually detected might not be a fully representative sample of all the pairs produced, potentially skewing the statistics in a way that could still, in principle, be explained by some cleverly constructed local hidden variables theory, exploiting these specific technical gaps. Closing these remaining loopholes, one by one, occupied experimental physicists for the following 3 decades, requiring extraordinary advances in photon detector efficiency, entanglement generation techniques, and the sheer precision of timing and distance measurement involved in ensuring no faster-than-light signal could possibly explain the observed correlations. This work culminated in 2015 in a series of experiments conducted independently by groups led by Ronald Hansen in Delft, and shortly after by groups involving Anton Zeilinger and others, that finally closed the major remaining loopholes simultaneously in what are generally called loophole-free Bell tests. These experiments used entangled electrons trapped in diamond defects, separated by more than a kilometer, with detector settings determined by genuinely random processes generated only after the particles were already separated, and detection efficiency high enough to rule out the sampling bias concerns that had lingered around earlier experiments. The result, confirmed independently by multiple research groups using different experimental techniques, was unambiguous. Bell's inequality was violated decisively and repeatedly, exactly as quantum mechanics predicted, with no remaining plausible technical loophole left for a defender of Einstein's local realism to appeal to. This body of work, Bell's original theoretical insight, followed by 5 decades of increasingly rigorous experimental confirmation, was formally recognized in 2022 when the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger, specifically for their experiments demonstrating the violation of Bell inequalities and establishing the reality of quantum entanglement beyond any remaining reasonable doubt. I find it difficult to overstate how significant this recognition actually is. In terms of what it settles about a question Einstein and I argued over for years without either of us ever expecting to see it definitively resolved. I want to be precise about what this experimental result actually proves, and equally precise about what it doesn't prove, because I think overstating a scientific result is nearly as dishonest as understating one, and I've tried to hold myself to that standard throughout every conversation I've had, reflecting on physics since. The Bell test violations conclusively rule out any theory that is simultaneously local and realistic, in the specific technical sense those words carry in this context. This means Einstein's specific vision that particles carry definite predetermined properties established before measurement, combined with the assumption that no influence can travel between separated particles faster than light, cannot be correct as a complete description of quantum phenomena. At least one of those two assumptions, locality or realism, has to give way, according to what nature has now unambiguously demonstrated through direct experiment. What remains genuinely open even now is exactly which assumption to abandon, and different physicists working from different philosophical starting points have reached different conclusions about how to interpret this result. The interpretation Bohr essentially advocated for, and the one most standard textbooks now present as the mainstream position, abandons realism, accepting that particles genuinely don't have definite properties until measured, that the act of measurement doesn't merely reveal a pre-existing fact, but actually participates in determining what becomes real. This is broadly consistent with what's called the Copenhagen interpretation, the framework Bohr spent so much of his career defending, and the one I found myself, during my own working life, more persuaded by than Einstein's alternative, though never with complete certainty on either side. But there are other interpretations that instead preserve realism while abandoning strict locality in a more limited sense, proposing that some form of non-local influence genuinely does exist between entangled particles, though crucially, this non-local influence cannot actually be used to send usable information faster than light, meaning it doesn't violate the deeper causal structure special relativity depends on, even though it does violate the stricter, more intuitive notion of locality. Einstein originally insisted any complete theory should satisfy certain interpretations, including versions of what's called Bohmian mechanics, developed originally by David Bohm, a physicist I knew personally, and whose own career intersected with mine in ways touched by the same political scrutiny that shaped so much of the 1950s for physicists with left-leaning political histories. Take this approach, preserving a form of hidden definite reality while accepting a specific, carefully bounded kind of non-local connection between entangled particles. I want to say something honest about what I think this means for the specific disagreement Einstein and I had all those years ago. I don't think either of us was simply straightforwardly wrong in the way popular retellings sometimes suggest. Einstein's deepest instinct that the universe should be describable by a complete deterministic theory, one that doesn't require probability and observer dependence sitting at its most fundamental level, has not survived this body of experimental work in its original simplest form. Local realism, exactly as EPR proposed it in 1935, is now understood to be incompatible with what nature actually does, confirmed not through philosophical argument, but through direct, repeated, loophole-free measurement. But I also think it would be a mistake to conclude that Einstein's discomfort with quantum mechanics was simply confused or unjustified. The specific alternative I find compelling, considering all of this from the distance of everything discovered since my death, is that Einstein was asking exactly the right question, using exactly the right kind of rigorous, falsifiable reasoning that good physics always requires, even though the answer nature eventually provided didn't match what he hoped or expected. He didn't simply assert his skepticism and walk away from the argument. He built, together with Podolsky and Rosen, the most precise possible articulation of what a complete theory would need to satisfy. Precise enough that 3 decades later, a physicist working from an entirely different angle could turn that precision into an actual testable prediction, one that finally allowed nature itself to settle the question directly. I think this is, in its own way, one of the most satisfying examples I know of how physics actually makes genuine progress over long timescales, not through one side of an argument simply winning through force of reputation or persuasive rhetoric, but through the argument itself, refined and sharpened by serious thinkers on both sides, eventually producing a question precise enough that experiment could answer it definitively, even if the answer took the better part of a century, and required tools and techniques neither original disputant could have anticipated, to finally arrive. What I find myself thinking about most, considering this resolution from wherever this reflection is coming from, is how thoroughly it validates something Bohr himself always insisted on. Even when Einstein pushed back hardest against it, Bohr never claimed to fully understand, in any deep intuitive sense, why nature behaves the way quantum mechanics describes. He simply insisted that our classical intuitions, the deeply ingrained assumption that objects have definite properties independent of observation, an assumption built into nearly every aspect of how human beings naturally think about the physical world, simply don't survive contact with what happens at the quantum scale, and that physics needed to accept this discomfort rather than insist on forcing quantum phenomena into a classical mold they were never going to fit. The Bell test results, decades after Bohr's death, as well as mine, have provided about as close to a definitive experimental confirmation of that basic insight as physics is likely to ever produce for a question this deep. Entangled particles genuinely do not behave as though they carry pre-existing definite, independently determined properties, correlated only through some earlier local interaction, the way any reasonable classical intuition would expect two correlated but separated objects to behave. Something about the quantum world resists that picture, stubbornly, consistently. Across every increasingly rigorous experimental test, physicists have managed to devise, right up through the loophole-free experiments that finally earned Clauser Aspect and Zeilinger, their Nobel recognition in 2022, I want to close by returning to something I said in our earlier conversation about this same disagreement, because I think it holds up even more strongly now that I've had the chance to walk you through how it actually resolved. Einstein and I disagreed for years, not because either of us failed to understand the mathematics of quantum mechanics, but because we disagreed about what a complete, satisfying theory of physical reality ought to look like at its deepest foundations. Nature has now spoken, decisively and repeatedly, and in a very specific technical sense. The universe has confirmed that Moore's willingness to abandon classical intuitions about definite, independent, locally determined reality was closer to how nature actually behaves than Einstein's insistence that a complete theory must restore that classical picture through some deeper hidden layer of variables. But I don't think that makes Einstein's resistance a mistake, in any sense worth apologizing for on his behalf. He asked the sharpest possible version of a question every serious physicist should have been asking, and in doing so, he handed the field a tool, the EPR framework, later sharpened into Bell's testable inequality. That made it possible to finally settle a question that pure philosophical argument alone could never have resolved. That, I think, is what real scientific integrity actually looks like, even when, especially when, the universe eventually answers against the very position you spent years defending. Einstein didn't get the deterministic universe he hoped for, but he got something, I think, that mattered more to him in the end than simply being right. A question precise enough, honest enough, and rigorous enough that nature itself could finally be made to answer it directly.